Hello everyone, Dr. Zia Tahir here. This video tutorial is about 3D heat transfer analysis in Abaqus, and specific topic is steady state heat transfer and transient heat transfer from base to tip along the fins. And that is a problem statement. A hot surface is cooled by attaching pin fins to it as shown in the figure. So the fins, they are attached to a base plate. The fins are 3 centimeter long, that is the length of the fin, and have a diameter of 0.25 centimeters. So that's diameter of each fin is 0.25, and are mounted on a square base plate having thickness of 0.25 centimeters. So thickness of that is 0.25. The fin center to center distance is 0.6 centimeter and the side of the base plate is 2.4 centimeter. The side of the base plate is 2.4. The fins are made of copper with thermal conductivity 400, density 9000, specific heat capacity 385. The temperature of base plate is 90 degrees Celsius and the temperature of the surrounding air is 20 degrees Celsius. The fins are cooled by air having velocity of 10 meter per second. That is a problem description. And then here is objective to determine temperature at the tip of the fins. So what is the temperature at the tips of the fins and along the length of the fin? So that is a problem description. So these type of fins, they are commonly used in these type of small fins. They are very commonly used in like the for electronic component and especially for computer motherboards. Like as you can see here, so these are square fins. They are being used. So usually what will happen practically, like when they are used in different components. So like this one, it is to cool down a processor, I believe. And for this case, the base is directly connected to the heat source, and then the sides, they are exposed to air. So usually for these type of component, and a fan is used to increase coefficient of convective heat transfer. So and usually fans are used. So fan at slow speed, so they will remove less heat. So convective heat transfer coefficient will be low. So for this case, like here, air speed is given, which is by a fan. So an empirical formula I found from the internet, and here you have that and that is on engineering toolbox page. So there is a formula to B, which connects convective heat transfer coefficient by air. So it uh, convert wind speed into convective heat transfer coefficient. So for 10 meter per second, I have calculated convective heat transfer coefficient as 32. So the convective heat transfer coefficient 37.2 is being calculated. So in this video, I have actually divided into two parts. So what I am going to do, I am going to model that 16 fins and then as well as a single fin to check that because the fins practically the fins they are symmetrical, uh, practically they or probably fins on the outer side they are if a fan is being used, so they have a little bit more uh, heat transfer rate compared to the inner one, but like all they are symmetrical along horizontal and along any of these axes. So they can be modeled due to symmetry as a single fin. So I am going to model that all 16 fins and then a single fin in this problem. I am using Abaqus 2020 for this purpose. So the steps which I am following, you can use in any newer version or older version of Abaqus. So here are three steps in Abaqus modeling, analysis, and results. So which you can see here, like here you have model, analysis, And in model module, you have model and analysis, and then you have result. So first, I'm going to show you how to model in Abaqus. So before modeling in Abaqus, you need to make sure that you are using consistent units, like as I mentioned in meter, temperature in degree Celsius, and thermal conductivity as watt per meter per Kelvin per degree Celsius, and coefficient of heat transfer as watt per meter square per Kelvin. And similarly, you can use that otherwise, others instead of degree Celsius, you are using Kelvin. So you need to make sure that your units are consistent. And if you are using conduction or convection, so for conduction and convection, you can any unit you can use. Like if you have thermal conductivity at watt per meters per Kelvin, and it doesn't make any difference if you are going to convert that in watt per meter per degree Celsius, because the equation, basic equation use delta T, and delta T is same in both degree Celsius and Kelvin. But if you are using radiation, so for radiation you have to use standard unit, which is Kelvin, and you need to convert all those units into the Kelvin. So for this problem, so dimensions are in centimeters, so they need to be converted into meters, and then rest of the units, they are pretty much what is required. So you need to set work directory where you can save all your model and results. So for this purpose, I have here, I am going to save that in chapter 13. So I just copy the link of that chapter 13 and then file set work directory. So I'm going to set that work directory here. So now the work directory is being set. So in the model, the first one is create part, which is create part, 3D deformable solid and extrusion. In Abaqus, this is modeled as first I'm going to model that base plate, and once the base plate is being modeled, and then I'm going to model those fins on top of it. So for that one, first in the model, I can go to the part module, double click on that part one, 3D deformable solid and extrusion, and approximate size of that. So approximate size is the double of the maximum dimension. The maximum dimension is 3 centimeters. So I can go for 6. So let's say 5 e raised per minus 2, 5 centimeter, continue. Then that base plate, this one, it is 2.4 centimeter by 2.4 centimeter. So I'll use that create line rectangles to sketch the base one and arbitrary dimension. And then that is 2.4 e raised per minus 2. And the other dimension is 2.4 e raised per minus 2. Okay, so then it is being drawn. So dimension 2.4 or 0.24 and 0.24 meters. So that's done. Cancel procedure and then sketch the done. And now it says that for extrusion, what are end condition? So the depth of that, so that depth is equal to depth of the extrusion is equal to the thickness of base plate, which is 0.25, which is 0.25 centimeter. So 0.25 e raised per minus 2, that is 0.25. So that base plate is now being designed, modeled. Now on that base plate, these fins are required, and for that one, they will form by extrusion. Here you have uh, create solid by extrusion. It says select the plane for solid extrusion. I am going to draw that here, and then a vertical and on right. So now that is you got. Now here is a region is in the center. So the total dimension is 2.4. So then each side is 1.2. I can see that from here, like, or I can add dimensions on that. Okay. So sorry, it's not possible, but I can see that here that this is 0.012. Now distance from edge of base plate to the fin is not given, so I'm assuming that it is cut from right from the center, so that center to edge distance is 0.3 centimeter. So I am going to draw that circle anywhere. So that is, if I'm going to draw on the top, so this one is the center of one of the tape fin. So now on that, I am going to draw a circle with arbitrary dimension, and then I'll give its dimension as it is, because the diameter of that is 0.25 centimeter. So its radius will be 0.25 centimeter is the diameter of each fin. So it is 0.125 centimeter e raised by 2 in, and that you got. Okay, so I don't want these dimensions anymore, like so. And that circle, reference circle, which I have just plotted before, I don't want it. So now I have drawn that one circle. Now there is a option in uh, Abaqus, so you can simply perform a linear pattern. So it says select the entities to pattern, so that are the selected, and that is selected, and now you can see that I want that four in both direction, but they are going in other way. So I'm just going to flip them. Okay, so and the spacing is zero point 0.6 centimeter, and the other one is also zero point 0.6 e raised power minus 2, and you can see that they are being created with symmetry. So done, and then this is the direction of extrusion, and because the total length of each fin is 3 centimeters, so that is 3 e raised per minus 2 meters. So then done. So now this part is being created. You can see that this part is being created, and then here are, that is a sketch of one of that. Okay, and then that is a sketch of the other one. Okay, and then that is extrusion for the okay, and then you can verify from here. The extrusion is 0.0025, and for that extrude length is 0.03. So now the part has been created. Now the next step in the Abaqus is to create Datum plane, and then on that create partition. This will help you to get better mesh. So for that purpose, here go to part module, tools, and Datum, and create a Datum plane for partition. And I'm going to set from principal plane, let's say from, so no, from a plane. So this is a plane, and the distance of that I want to create that partition passing through the center of each tip in horizontal and in vertical direction. Okay, so for that offset from plane, so that plane is be selected. Enter value, it is because I want to go in the other one, so flip it. Okay, and then the direction of that is zero point 0.3 e raised power minus 2, and you can see that it is created right in the middle of, so in the right in the middle of that. Okay, so I can create one more plane offset from a plane, but this time I'm using Datum plane. Enter value, and that flip is okay, so that is zero point 0.6 e raised power minus 2 that you got. So in the similar way, I'm going to create Datum planes for in other 6 directions. Now the Datum planes are being set there. The next one is to create partition, and for that one is tools, partition, and partition phase using Datum plane. So select the faces to partition. I'm going to select that whole model. Done, and then select any Datum plane, and then create partition. You can see the partition. So in the similar way, I'm going to create partition for all those. So in the similar way, I have created partition for all those partition through the center of the fin in both vertical and horizontal direction, and that will help to select the nodes and then help to create some uniform meshing. Next step is to create surfaces, and surfaces geometry type to apply temperature and H. So again, what is going on? The heat, when the fins are attached to the base plate, so the base plate lower part of base plate is only exposed to the temperature, and rest of the fins they are exposed to air. So for that one, need to create surface for all that part which is exposed to air, and for that purpose, a surface in the part module, tool, surface, and then create a surface, and the name for that is fins. Continue. So for that one, I am going to select all the everything and just deselect. I'm going to select all that and just to deselect the lower part. So with the control, you can deselect, and with the shift, you can select again. So now whole base is being deselected. Okay, so done. So now in the parts, and then here you can see that surface is being created. Now the next step is to create set a geometry type to apply temperature, and for that one, here you can see set a geometry type, and I am going to name it as base. Continue, and for that purpose, I am going to select its base. So with the shift, you can select that. So now the whole base has been selected. So done, and here in the set, that is the base. And that base is being selected, and then these are the fins, they are selected. Okay, next step is to create material. So material is copper with thermal conductivity 400, density 9000, and specific heat capacity at 385. So, so now in the property module, material, it is copper. In the journal, density, that is 9000. In the thermal conductivity, then it is 400. In the thermal, then specific heat, 385. So that material is being created. Here you can see that the material is being created. Double click on that, and conductivity 400, density, and then specific heat capacity. Okay. Now the next one is in the property module, create section and assign section. So in the property module, here you have create section. The section is solid homogeneous and that copper, and then the next one is assign section. So section assignment here, no need to create any set. So done, and that section is being assigned. Now the next is in the mesh seed part, assign mesh control, mesh part, and assign element type. So here in the mesh module, seed part, and then I am using it as 0.5 centimeter. So 0.5 millimeter, 0.5 millimeter. So apply, because the base is okay. And then here assign mesh control. I'm using tetrahedral stress element, and then free. Okay, and then mesh. So this one is being meshed. So the part is being meshed, and then here assign element type. In the family, it is heat transfer, and standard quadratic. It's a 10 node quadratic heat transfer tetrahedron. So here is all that done. So mesh is done. Then the next is part, create set node type to plot temperature distribution. because the required is temperature at the tip of the fin and along the length of the fin. So for that purpose, uh, need to create one set right in the center of it here and one along the length. So any node can, any fin can be selected. So in the set, I'm using node and that is on the tip. Continue and right in the center of the tip. So that is selected, done. One node is selected and the other one is, it is along length node and here make unsorted set. Continue and then you can, here you have a long edge, add before and then here, so any edge can be selected. So I am going to select an edge along that where I have created partition. So done, and it is showing me the arrow of that sequence from tip to the base, but that is not required. I'm going to flip it along the direction of heat transfer, so that yes and okay. So now here you can see I have selected one at the tip and one along the length. Okay. Next step is to create instance, and for that one in the property module, in the module assembly, create instance. Okay, so that property, so it is being assembled. Now the next one is create step heat transfer, and initially I'm going to do it for steady state when for the temperature equal 1 second. So here in the step module, create step, and I'm going to name it as heat transfer. Heat transfer, and then heat transfer continue, and then steady state, and then time period is 1. Okay, so now it is being, step is being created. Okay, the next one is load, create boundary condition and temperature. So this, so the base is exposed to the temperature of 90 degrees. So then we will just create a boundary condition for temperature. So for that one here, you can go boundary condition, or even in the load module, you can use here boundary condition. So boundary condition, I am going to use it as base, and step is heat transfer, continue, and I have created a set for base that is a geometry type, and then the temperature is 90. Next step is create interaction to apply temperature and T and H. So ambient temperature is 20 degrees Celsius and convective heat transfer coefficient is 37.2. So that one, for that purpose, here interaction, or you can find it here, and I am going to use it as name as air surface film condition, and I have created a surface for that already called as fins, and film coefficient, it is 37.2 and sink temperature is 20. So okay, so now that thermal boundary conditions are being applied. So the modeling steps, they are done. So the next one is to create a job in analysis, create job, data check, and submit. So I'm going to rename that as multi fins. Okay, that is the model name, and here create a job, and job is model fin underscore steady state SS. Continue. Okay, so on the job, first you need to submit data check, and then it's, once data check is complete without any error, so then the next one is to submit job. So the data check is completed without any error. So then submit job, okay, and then that job will take some time to finish, to complete. It is being submitted and then it's running, and it will take some time to complete. The job is completed. Now, once that job is completed, so the next one is results. And in results, common options of visualization. So here, results, and that is the temperature gradient, that is the heat flux, and then it is the nodal temperature. Okay, so next one in the tools, create path and node list to arrange the nodes of the orders. So to show that, so first one, it is go to create XY data, ODB output, continue, and here unique nodal and nodal temperature for that is you have tip. So plot it, and then I'm going to save that data. So that data is being saved here, and I'm going to rename that. So that is T underscore tip. So temperature underscore on the tip. So the tip temperature is 85.134. And the other one is along the length of the fin. And for that one, uh, need to create a path. So for that one, tools, path, create a path. And from the node list, okay, so I am uh, name it as nodes along length. So continue. Okay, so then in the part here, I have here length. Okay, okay, let me dismiss that one. Go to and then add before. So now that nodes are being selected. Okay, and then here path in the XY data, I have created a path, continue, and then here, okay, so plot, and you can see here that is the temperature, and I'm going to save as. So this one is T underscore length. Okay, so now that is the tip, temperature along the tip, and then temperature along that, and I'm rename that underscore steady state, and that one rename it as underscore. Okay, so now here you can see that the temperature, maximum temperature is at the base is 89, and at the tip it is 85, and that is this one is along because I have selected the node. This is the tip of the fin, and that is the sorry, base to tip. This is 3. So that one is 0 to 3, and that is the temperature distribution. Okay. So now this is steady state done. Now I'm going to do it as transient. So for that purpose, now I'm going to change that step to heat transfer, transient, and the time step I'm going to use at 300. So for that purpose, here double click on step. Now it's transient, and the time period this time is 300, and I'm going to use that fixed. So number of steps are 300, and then increment size is 1. Okay, and now I am going to rename that as here multi fins underscore transient, multi fins underscore transient. Okay, okay, and then it is being submitted. Okay, so it will take some time to complete. So now, as it's going to complete, now I'm going to model that a single fin due to the symmetry. So now its base is zero point 0.6 by zero point 0.6 centimeter. So I'm going to model that as a single fin. In the meantime, it is, and then I'll compare results between steady state and transient, and then multiple fins and single fin. Now I have modeled that single fin, and assuming that the temperature, sorry, all of its parts are exposed to air. So now here is the single fin, and I did here, that is a sketch section of it. Okay, so each dimension is 0 0.6 centimeter. Then on that, I have created a section like that one, and then this is the model. Uh, then the steps for that one, I have created a partition, these two partitions there, and then mesh. I kept the same mesh size, 0.5 millimeter. Then I have to apply uh, temperature. I selected its base, and to apply temperature and heat transfer coefficient, I have selected all that part, and then on the tip, I created a node set and then another node set along the length. And then the material is the same, copper, with thermal conductivity 400, density 9000, specific heat capacity. And then now the step is steady state. And then here for air, I put a value of H and T, and for the base plate, I have applied the temperature. So now for the steady state condition, for single fin steady state, I name it. So here are the results for that single fin steady state. So here you are. So now I'm just going to compare that, how much is the difference between multiple fins and single fins. So I'll go to the viewport, I create a new viewport, and then a viewport tile horizontally, now viewport tile vertically. So here I am going to open in the left viewport, I'm going to open that multiple fins steady state condition, and here it is single fin. So for this one, let's say the gradient. So that is the gradient. So the gradient in both of these, so the maximum, there is a slightly difference between the gradient in both of those. Okay, and then heat flux, and here click here on the top of that, and then that is the heat flux. So heat flux is also changed for that one, and then nodal temperature, and then the nodal temperature is like 90 on the top. Okay, and then maximum is 90 and the minimum is 85.127, and here is 90 and minimum is 85.123. So there's not much difference. And for this one, I have created now a comparison between, for both of these, I have made a comparison of the temperature at the tip. So here is a single fin, that is a single fin temperature, single fin, okay, temperature at the tip, and then here is the single fin temperature for like along the length, and here is for both. So this one is this one, is for multiple fins and that is for single fin. So I'm going to plot them side by side. So along the length, so these two are being plotted, and in here I am going to plot that at the tip. So you can see that there's not much difference in that, but these two graphs, if I zoom it very well, so then there is a slightly difference between them, and that, let me check that how much is the difference. Okay, so that is for single fin along the length. Okay, single fin along the length is viewport again, tile vertically, and that is correspond to this one. And here I am going to plot that multiple, that is multiple fin along the length, and then now for the both ones, so this is for the multiple, it is 89.77 and the other one is 87.5.12, and here is 86.7. So if you are going to round off them to four significant figure, or you are going to round them to decimal places, so the results are same. So what's the conclusion then? The conclusion is that you can model uh, a single fin, and for that one the results are not too much different. So that is a comparison. So the results are not too much difference, and they are accurate up to four significant figures for temperature, but definitely for heat flux there is difference. Now going back to the transient heat transfer of multiple fins. So here is the multiple fins and then heat transfer. Like I have used transient with the time period of 300, and then it is still running. Let's monitor it. So like as it is around 45 minutes, I have set it into running, and then it will take some time, but still let me check that how much is being done, or if the solution is being converged. So even for that 78 increment, or for 78 seconds, I am going to do it like multiple fins. Okay, results. Okay, now what's going on? Previously, we have here like as on the tip, so there is a single value. But this time for this one, when I'm going to plot it along the tip, so then there will be multiple values. Okay, so first before plotting it, let me check that what is the difference between steady state and transient. So in the viewport, I'm going to create a new viewport. Okay, and then tile them vertically. Okay, so now here is transient, and here I'm so transient there, and I'm going to with multiple fin. Then here I'm going to open that. Okay, so like as so it is visible like this way. Okay, so now this is a steady state. So I am going to plot that temperature here, nodal temperature, and then nodal temperature here. So you can see that the minimum uh, for steady state and then for transient, that is the same one. Okay, and even for that, how many it reached till 81 steps. So that solution is being converged. So now I'm going to plot that temperature at the tip of it, let's say. So this time it is being plotted versus time. So this time it is being plotted versus time. On horizontal axis is time and the vertical axis is temperature. So I am going to save that one. It is here for node 232. That one I am going to rename it. So now that plotted multiple fins transient on the tip. So here you can see that the solution is start converging like after somewhere after 30 minutes. And here I have these like the maximum temperature as 85131, and for that one it is it is again is the same. So let's say like the maximum temperature for this one, because the time step is 1 second and it is increasing linearly, so that is 85.131, and then like 85.131, that is the same one. So it will take some time, but I can see that after 30 seconds, after 30 seconds, the solution is being converged. So this is all about steady state and transient heat transfer of a fin. So let me repeat that steps again. So I'm going to repeat that in the first part. First thing, you need to create a part. So for that part, first is base is being drawn. First is the base, and then is extrusion being performed. And like for better node, then partition is being created. So then surface is being created to apply a thermal load, and then here another set is created to apply temperature, and then few nodes are selected for some plotting purpose. Then a material is being created by giving it conductivity, density, and specific heat, and then step is being created, and steady state and transient they can be used. Okay, and then interactions are defined, and interaction are to apply ambient conditions, and then boundary condition is being applied for temperature. Okay, so then we got two different types of results, and for those two different types of results, when I'm going to when compared when those compared steady state, and then when steady state and transient they are compared. Okay, so steady state and transient, so you'll get like transient state that converge after some time, and then it become steady state. And then multiple nodes, multiple fins, when they are being plotted against, like when the multiple fin and a single fin are compared, so you can see that the temperature distribution is almost the same. That is almost the same. So this conclude that you can, instead of going for multiple fins, so you can just model it as a single fin. And then steady state solution take less time, computation time, and transient solution takes more time. So that is all for this tutorial. I hope that you understood the difference between steady state and transient. And then for symmetrical problem about axis of symmetry, you can reduce a numerical model into a simpler one. And then uh, you can compare the results. So thank you very much for watching this tutorial. And you can leave comments for your feedback. And if you want me to solve any other problem in Abaqus, you can comment. Thank you very much for watching again.